Hi again. Our next reaction is allylic halogenation, and actually the cartoon up here is part of the mechanism for allylic halogenation. When you think of the allylic carbon, remember that's the carbon that is off of the double bond carbon. So it's the carbon directly attached to a double bond carbon. So this is the allylic position. Eventually we're going to get a bromine at that position, but just like with allylic carbocations, you know that you can have resonance with allylic systems, and we're going to see the same thing here in this radical reaction. The thing is, there are two ways to do allylic halogenation. We're going to mainly do, or exclusively use, just bromine, and we could add the bromine in the allylic position using two different reagents, either Br2 or NBS. Let me show you the first example, or actually let me talk about allylic carbons. Quick review. If you have a double bond molecule like an alkene, okay, that's good enough. Let's mark all of the allylic carbons. So the allylic position, we have three of them actually, here, here, and here. So there are three allylic carbons there. Now, if we think about an allylic radical, and we'll do something a little more simple. Okay, let's take a look at that alkene, and let's convert it into a radical. We'll show this in a mechanism later. This allylic radical has resonance, and the resonance, actually before we do this resonance, why don't you test yourself? How would you draw the resonance for that allylic carbocation, but also allylic carbanions, right? If you feel like you could draw me the resonance by drawing the mechanism arrows, go ahead and pause the video. Okay. So for each of these last two cases, we're going to move 2 electrons. Resonance, you're mainly going to move either a pi bond or a lone pair. For these two examples. For the radical, we're going to obviously move an unpaired electron. But see, there's no lone pairs here. So we're going to shift the strategy is to shift the pi bond to neutralize that carbon on the second carbon. And we get this. Okay. It's still allylic. Okay, so I know it's primary, but it's primary allylic, and it does exist. Okay, it's not as unstable as just a primary carbocation. The trick with anions is to take the lone pair of the anion and shift that somewhere, and we're going to shift it to make a pi bond here. That carbon now has 5 bonds, so let's resolve that. Okay, so this will require 2 mechanism arrows, and then we have this. In either case, we spread out the charge. So resonance, again, you recall, is a stabilizing effect. Well, look at the pattern. The pattern is we shift the double bond and we put the plus charge or the minus charge on the naked carbon. The carbon that doesn't have 4 bonds. Therefore, you could probably predict that that is your second resonance structure. Now, could you draw the mechanism arrows? Don't forget, this is an unpaired electron. We're only moving 1 electron at a time. Therefore, we're going to use fish hooks. Okay, I'll do this in pink. You know that unpaired electron at the very end came from a pi bond, so we'll just put 1 of the electrons of the pi bond there. But we also made a double bond in between the 2 middle carbons. So we're going to do that by pushing that electron to the bond, and then the second electron of the pi bond goes there also. So you know that 2 electrons make a bond. That's how we get the double bond, because we added these 2 electrons. Okay, it's a little more complicated, as you can tell, because you have 3 mechanism arrows, because we're only moving 1 electron at a time. Okay, shall we go on to the reactions? I think we're good. Let's move on to the first allylic halogenation reaction. Okay, to do an allylic halogenation, you obviously need a double bond, or else you don't have an allylic position. And I will choose, for now, the cyclic alkene. Cyclohexene. The reagents here are going to be Br2, and light. See, that should be very familiar. If you saw the first reaction that's usually covered in radical reactions. This is the same reagent as radical halogenation, right? Radical halogenation. So this is where the unit becomes very, very tricky. Okay, if you recall, I'll put here review. You see how you got to be really conscious of your starter material, because it's the same reagent, but now we have an alkane. And when you have an alkane, remember you replace the hydrogen on the most substituted carbon. They're all secondary carbons, and no matter where you put the bromine, it's the same product. But let's go back to our new reaction, allylic. Your allylic positions are where? Here and here. It doesn't matter which one, because they would give the same set of products. So the same set of products, I'm just going to put the Br up here. It has to be allylic, so you're not going to get rid of the double bond. Because we're going through a radical mechanism, and the radical, as you know, is sp2 hybridized, that carbon, we actually have the situation where that bromine can add from the front or back. So actually, we don't have one product, we have 2 products that are enantiomers of each other. So depending on your professor, they may want you to be very specific and draw all the products, including different stereoisomers, or in this case, different enantiomers. Or your professor may say, as long as you get the correct product, or you put the bromine in the correct position, we're good. Okay, so either this answer or this answer, where you have to account for stereochemistry. This one, it's achiral, right? We have no chiral carbon, so no wedges and dashes here. So that's allylic halogenation. There's another way to do this, and that's using a reagent called MBS. I don't think. The reason why people like MBS is it actually avoids, what other reaction do you know with Br2 and an alkene? See, this is so tricky, because we're seeing Br2 over and over again, but depending on the conditions or the starter material, we get different products. Remember this? Br2 under chlorinated solvents. This is halogenation. We literally just add 2 bromines. Oh my goodness. And remember, this was anti-addition. Okay. This is all review for this reaction, anti-addition. Okay. Survey what is on the screen right now. Br2 in light, with an alkene, you get this product. Br2 and light with an alkane, you get this product. What's the difference between these two? Okay, so these two, we didn't talk about it, or at least I don't talk about it when I talk about the alkene reaction, addition reaction, but this is normally run in the dark or cold, because what are they trying to avoid? If you're trying to make this dihalide, you're really trying to avoid this. And if you're trying to make the allylic halide, you're trying to avoid doing this. So here you use either light. Whenever you could use light, you could use also heat. That actually indicates that you're going through a radical mechanism. That's a very good clue that you're going through a radical mechanism. If you go through a radical mechanism for an alkene, you go ahead and hit or make the most stable radical, which is the allylic radical. This is not an allylic reaction, okay, when we went over alkene reactions. So you just got to be very careful. You really got to know your Br2 reactions inside and out, because I see 3 already. 1, 2, 3 that are all different. So that was an aside. Let's take a look at NBS. NBS in part is preferred because you won't get this ambiguity when you have an alkene with Br2. Okay, because NBS won't do this reaction, won't do the addition reaction. NBS is N-bromosuccinimide, and it looks like this. You may or may not, I don't require my students to memorize the structure. N for nitrogen, bromo, succinimide, NBS. Okay. And it does exactly the same thing as Br2 and light when you react with an alkene. So again, we can see this allylic halogenation as such. Okay. I'm not going to put NBS over the arrow. You can if you want. I don't think it's necessary to put light, but actually I'm going to say it is necessary to put light or heat, because we do have to form radicals. And again, I'm not going to worry in this case about stereochemistry. This is your product, okay? But it would make technically a racemic mixture because the Br can be front or back. Okay, so there are 2 ways, again, to do allylic halogenation. One way is with Br2 and light or heat, and the other way is down at the bottom with NBS. I would suggest that when you have a choice, like for a synthesis problem, and you have to say the reagent, I would use NBS. Okay. Okay. Now we're not going to do the mechanism just yet, because I chose a very simple alkene. Because this alkene here, it has 2 allylic positions, but either one will give you the same set of products. But what happens if you have several different allylic positions? Like for instance here, like where do I put the BR? Do I put the BR on position 1, 2, or 3? They're all allylic. Not only that, it's going to get a little bit complicated. We also have resonance, what we said at the beginning. Well, what does that do for us? Well, it actually gives us a mixture of products, because the bromine now could go on 2 different positions. Should I say 2 different positions? I should say 2 different carbons. They're both allylic, but because the double bond shifted, we get a new allylic carbon. Okay. We're going to take this stepwise, okay, and do a couple examples. Okay, the first example, where you could potentially get a mixture, is this one right here. Okay. Good old 1-butene. The one that we drew resonance for at the beginning of this video. I like NBS, so I'm going to do NBS. NBS in light or heat. Okay. Before you jump into the products, analyze what you have in the starter material. I have one allylic position here. I have one allylic position here. That's where a bromine can go. Okay, so that's the B in NBS and bromo. That bromine is transferred to that allylic carbon. Now, the issue is, I'm not going to worry about stereochemistry right now. The issue is we have resonance. So either on a scratch sheet of paper or underneath your problem, we're going to have this intermediate. So I didn't really show yet with a mechanism how we got this intermediate radical, but when we talked about radical halogenation, we made the most stable radical. In this case, the most stable radical is going to be the secondary allylic. So we did do, if you remember, what's called a hydrogen abstraction. Notice I didn't say proton, right? Proton, you leave behind the electrons. Hydrogen abstraction, you actually take its single electron with it. Okay, you could review your notes and just verify that. We practiced resonance at the beginning of the video, right there. Okay, so I'm not going to draw the mechanism. I just know that we get a new radical on that carbon. That's the other product. You notice that this product that I first drew came directly from the radical that we initially got, but from the resonance radical, from the radical coming from resonance, we can make this product. Okay, and you could have drawn the bromine going to the upper right. I just like this one, I drew it straight down. These two are the products, and they are they're both valid. But in terms of, let me double check. Yep. In terms of the major product, this is where it gets a little bit tricky. You notice that this is a secondary allylic, and this is a primary allylic. True, this is the major contributor in this resonance. But when you decide the major product, you don't go by the radical stability, you go by the alkene stability. Man, I don't know if I actually mentioned this before, but let me go over alkene stability. So this is a major because it's the more stable alkene. I think I usually talk about alkene stability when I talk about making alkenes, not using them. But I'm going to have to talk about the stability a little bit here. Stability of an alkene depends on the number of groups that are attached. So tetra substituted is greater than, and this is stability wise, greater than tri substituted, greater than di, and actually there's two main types of di substituted, cis and trans. And in this case, I'm going from higher stability, so trans is more stable than cis, di substituted. Okay, followed by mono substituted. So what am I talking about? You could either count the number of hydrogens or the number of groups, because on a double bond system, on a carbon-carbon double bond, you actually have 4 locations to put groups. You could put a group here, put a group here, put a group here, put a group here. So I'm considering hydrogen not as a group. So there are no hydrogens on the carbon-carbon double bond. Now you could have this more complicated if you want. It doesn't matter. It still means that you have 4 things on the double bond carbons. And if you want, you could put your dots. A dot here and a dot here. 4 things attached to those dots. 4 groups. Tri-substituted. If we remove one of those groups, it doesn't matter which one, but that's tri-substituted because we have 3 groups and 1 hydrogen. Di-substituted trans. Okay, let's do this one. Okay, versus di-substituted cis, which is a little less stable because of sterics. Those 2 carbons with their hydrogens, particularly the hydrogens, are very close to each other when you force the 2 groups to go in the general same direction. Then mono means your double bond is at the end of a chain. That's mono. You notice that there are 3 hydrogens. Okay, 3 hydrogens, 2, 2, 1, 0 hydrogens. Again, go ahead and put your dots if you want to emphasize that. How do we establish something as a group? It's connected to one of these pink dots. Okay. Well, look at the mixture we get. Okay, we get 2 compounds, and we normally have to pick the major product based on the stability of the alkene. So that's one complication. Even though we only had 1 allylic carbon, we get 2 products. How come we don't get more products here? Because if we made the radical here and we did resonance, okay, do it for yourself, you'll actually get the same product. You'll just have the bromine down here, but the double bond will be still allylic. It will still be an allylic bromide. So you could go through the resonance. You'll end up with the same product, actually. Over here, my 2 resonance structures are literally different. I mean, visually different. And they would lead to different, okay, draw this dotted arrow. They would lead to different products. One more example. This is going to be tricky because now we have definitely 2 allylic carbons. We have 1 here and 1 here. Okay, and they both have a hydrogen, so we could draw a radical for either of them, and we can call this position A, position B. Okay. The first thing is I want to choose which hydrogen I'm going to abstract. So if I'm going through this a little bit quickly, but if I choose A, I'm not doing mechanisms. I'm just showing you where the potential radicals can be. I get a radical there. Okay. I would have to know the resonance. Double bond shifts, and the radical happens on the carbon that's naked, the one that lost a bond. So that's A. This is B. Okay, you could pause and see if you could do B for me. Start with a radical on that carbon. Go ahead and pause now. Okay. We abstract the hydrogen on that B carbon, which is allylic, and then we draw the resonance. There. We actually have to choose a winner, and then we'll draw the products, and then we'll pick the major. So it's several steps, but the first step is choose A or B, because they're all different. Okay, I think they're all different. So this one is tertiary. They're all allylic. So I'm not going to say tertiary allylic. I'll just say tertiary. This is secondary. This one is primary, and this one's secondary. Okay. Hopefully, you know how to determine primary, secondary, and tertiary quickly. On average, A is the winner because you're averaging a tertiary and a secondary. Remember, the hybrid is a combination. The hybrid here is a combination of primary and secondary. So when I draw the products, I'm going to use A, and my two products are going to be this. ER plus ER. Okay? Those are my two products. And they're coming from the more stable radical. Right? This is the more stable radical. I'll put it here. It's a little bit of semantics, but it's so important. When I say radical, I'm not looking at 4 individual radicals, because you know with resonance there's only one radical. It's just a combination of these two. So there really is only 2 radicals. Radicals coming from the abstraction at carbon A, and radicals coming from the hydrogen abstraction from carbon B. So we have radical A and radical B. And from radical A I get the 2 products. Which one is the major product? This one's the major product because it's more substituted double bond, more substituted alkene, and specifically it's tri-substituted. Tri-substituted. Okay. Okay. I'm not going to do this example with you because I do want to kind of at least introduce. I do want to introduce the mechanism, but I'm not going to get through all of it. But the example that I want to show you is this one here. Okay. I kind of drew it kind of sloppily, but that, there, and there. Okay. I'll use NBS again. Okay. So I'm not going to do the mechanism here. For my class, they're not required to know the mechanism. Okay, but they should know that you form radicals and you try to form the most stable radical. I have 2 allylic positions. I have one here and I have one here. Allylic. But what do you notice about this allylic here? There's no hydrogen to abstract. So there's no H. So we really only have one position, and that position is right here. So let me draw this stepwise by drawing the 2 radicals. So your first radical is on this carbon down here, right, for this arrow, and then when you do resonance, you have this. Right there. Okay. I'm not going to draw the mechanism. You could always go back to the beginning of the video. That's how you show resonance for an allylic radical. Oops, bunny ears. Okay. So our 2 products are these 2. Uh-oh. Are we going to get the same product? Double check my work. Okay. So those are my 2 products because they're coming from my 2 radicals. Okay. I know I'm saying 2 radicals, 2 resonance contributors to the radical made by abstracting this hydrogen. Okay. Those are your 2 products, and do we have a clear winner? This radical is, this alkene is di-substituted. Put your pink dots. 2 groups, 2 hydrogens. This one on the right is actually tri-substituted because we only have 1 hydrogen and 3 groups coming off the pink dots. Again, our major product happens to be tri-substituted. Okay, no mechanism, but you do have to understand where the radical is being made, and do doing resonance give you different products. In most cases they do. Then you would want to pick the major product based on the stability of the carbon-carbon double bond.